So since we're able to use the noble gas core abbreviations, that's really the first thing I would look for. So I'm going to identify where that element is, and I'm going to try to figure out basically the closest noble gas without going over. So like Price is Right rule. So what's the noble gas that has not more electrons, but just underneath? So for my first one, I'm doing CS. So I can identify here, it's atomic number 55, so I know I better have 55 electrons in it when I'm done writing. What was the noble gas right before that? Yep. So we put that in brackets to say we want all of the electrons that are in there, and then all we need to add are the additional electrons. And since xenon has 54 electrons, and cesium has 55, we really only need to tell you about the location of one electron, and where is that one electron? It's in an s orbital. Which number s? Yep. And you can just number them down like this, and you can see that it's xenon 6s1. So that one should have been pretty easy lead off. Any questions about where I'm getting those numbers from? All right, let's do one that's a little bit trickier. So let's do nickel. So there's nickel. What noble gas am I going to start with? Argon. Yep, I got to go all the way back to argon. And then after argon, just work with me. What's next? 4s2. 3d, and how far in do I need to go for that? And that's pretty much it. Okay. Moving on. Okay, so this one is going to be pretty similar to nickel. What's the maximum I can put in the 3D? 10. And then where do I go after 3D? Goes back up to 4p. And how many over do I need to go to get to selenium? 4. So any questions about how to do those? Yeah. Yeah, I'll do that one. The other ones are pretty straightforward. So uranium is fairly ugly, and there's a little bit of confusion about how uranium works. So if you identify uranium, it's all the way down here at 92, and if you have a different periodic table in front of you, it sometimes is really obvious where these things underneath fit in. But remember that we just put these things on the bottom to kind of save space when we print that in a textbook. They really fit in this periodic table right about here. Okay, so you can see that 57 goes to 58 and 89 goes to 90. So when you're doing the configurations for these, you have to think back to where it fits back in numerically. So if uranium is number 92, what noble gas can I go back to for that? Radon. Yeah, I can go back to noble gas with 86, which is radon. Okay, after radon, the next place I go is into the 7s. So radon's 86, 7s, that's francium. So I go into there 2 spaces, all right? Do I have to go into the D block at all? Yes. I have to go 1 space into the D block because I have to go through number 89. What's the number of that D block? Yeah, since it's 7s, that's 60, so I'm going to get a 6D1 from there. And then I need to get into this block, and what is this block called? F block. And if I'm at 7s2, if I'm at the 6D, what F block number is this? 5. So the first time the F block shows up, it's a 4F, which means the second time it's a 5F. So how far into the 5F block do I need to go to get to uranium? 3. Okay. Different textbooks are going to put these in a different order, right? It would make perfect sense to me if you went radon 7s2, 61, 5f3. That would make sense to me because that's how you read it through on the periodic table. Your book is putting them in a slightly different order, and your book is just doing that based on what it knows about kind of where the energy levels are. So let me make sure I have the right energy levels for this. So your book writes it as 5f3, then the 6d1, and then it writes the 7s2. Okay? So as long as you understand where all of those numbers come from, you're in pretty good shape. The reason it's writing it like that is because if we think of the N, right, the principal energy level, it makes sense that 5, then 6, then 7. That's why your book is writing in that order instead of how it kind of runs through on the periodic table. Questions about uranium? 7.45 is related to these, so I'm going to skip there next. So what I like to do when I start these is I like to start by writing out the neutral configuration and then just trying to figure out how it changes when it becomes an ion. So if we were going to write out the neutral configuration for cobalt, what noble gas could we start from? Yep. Argon, and then what's it past that?
4s2.
Then we go to 3d7, right? So seventh one in. Okay. So in order for it to become the 2+ ion, how did it do that? Yeah, so now we need to lose 2 electrons. So when we lose 2 electrons, where do we lose them from? The highest energy level orbital. And how can I tell if I'm dealing with the highest energy level orbital? What am I looking for to know that it's the highest energy level orbital that those electrons are in? So usually it's furthest on the right, yes. Do you guys remember talking about like N, L, M sub L, M sub S? Which one of those tells you the energy level you're dealing with? N, L, M sub L, M sub S. Which one's the most important one? Tells you the energy level you're dealing with. N, L, M sub L, M sub S, which is the first one that tells us the energy level we're in. N is the principal quantum number, right? It tells us the energy level we're dealing with. N comes up at the beginning of these. So 1s is the first energy level, 2s is the second energy level, 3s, 4s, and so on. So if I've got a 4s and I've got a 3d, which of those is actually higher energy? The 4s is actually higher energy, which is what's a little weird. So since this is actually higher energy, when I make that 2 positive ion, when I lose 2 electrons, I'm going to lose them from the highest energy orbital first. So when I finally get this down to being my ion, it's actually just going to look like Ar 3d7. So those 4s electrons will just be gone because I've lost the 2 electrons from the highest energy level orbital. This is mostly a problem when you deal with transition metals. So transition metals are going to lose their s electrons before they're going to lose their d electrons. And that's because those s electrons are actually in a higher energy orbital than the d electrons. Any questions about how that worked? Okay, let's move on to tin. So here's tin. What noble gas can I use for that? Okay, and if I was just writing out the normal full electron configuration, after krypton I would write what? 5s2, then I'd go 4d10, and then I'd go all the way over to 5p2, okay? But how did it get to be tin 2+? Yeah, so it's still going to lose 2 electrons, but where does it have to lose them from this time? Why is it going to lose them from the p? What's different about this? How is this different from the first one? So if you're comparing 5s and 5p, how do you know that the 5p is higher energy? All right, but so in this case, you can kind of go back to the idea that further to the right are your higher energy electrons. So once we get to the p orbital is higher energy than the s orbital. So if we wrote this out, it would just be krypton 5s2 4d10. Questions there? All right, let's try the ZR4+. All right, so find it. So let's see if we can maybe figure this one out without writing the whole neutral one out. All right, so we know that it goes to krypton, it's got 2s electrons here, it's got 2d electrons here. How does it get to be a 4 positive charge? It has to lose how many electrons? 4. And where do those 4 electrons have to come from? It's going to lose its 2s first, and then it's going to lose the 2 from the d. So when I say 2s, I mean the 2 electrons in an s orbital, not number 2s. So it's going to lose all 4 of these electrons. So if it loses all 4 of these electrons, what would the symbol be? Yeah, so we can actually just write that out as krypton. Questions there? All right, silver's a kind of tricky one, Ag, so I'm going to give you about 20 seconds to check with someone near you, see if you got the neutral one, and then see if you figure out what it looks like as an ion. Go ahead and talk to somebody, it'll be okay. All right, so your neutral configuration for silver should be krypton 5s1 4d10. Why is that the correct neutral configuration for silver? What do you know about silver? What do you know about copper? It will when it becomes positively charged, but when we just filled a neutral one, you should have learned that silver half fills its s orbital, and then instead of having only 9 electrons in its d, which is what it should have because it's 9 in, it actually moves one from the s into the d because it's more stable having a full d shell. So it promotes one from the s into the d, which is why its neutral configuration looks like that. So if it becomes positively charged, just like we've seen before, what's going to happen to its electrons? If it has a +1 charge, it must have done what? Yep, so it's going to lose 1 electron. So if we write this out, we can just write it as krypton 4d10. So does it make sense why I sometimes write the neutral first and then lose the electron from there? Because for ones that have weird filling orders, that actually makes a little bit more sense. All right, so let's talk about the last one. This one's, again, a little more straightforward. So we see sulfur over here. How did sulfur get a 2 negative charge? How did it do that? Gain 2 electrons. So it now has the same number of electrons as argon, so I can just write argon. That's it. So that's all for that one. All right. Any other questions I can answer about electron configurations? All right, I don't want to short you guys time on the quiz, so I'm just going to briefly talk about periodic trends, because that's what 7.25 is about. So we can just use the periodic table that's up there. What do you guys remember about the general trend for atomic size, or atomic radius? Where do we have the largest elements? Okay, so why does it get larger as we go down this way? Yeah, more energy levels, more shells, however you want to use it. So it gets larger and larger and larger, okay? What about this way or this way? Which way is it going to get larger? Why is it going to get larger back this way? Okay, so you remember reading about Z effective in your book, but basically if you think about everything that's in the same row on the periodic table, it's essentially got everything kind of with the same core electrons, but as we move across the periodic table, we're adding more and more protons. And what do you know about the charge on protons? They're positive, and what do positive protons do to negative electron clouds? Attract them, okay? So as we have things in the same kind of shell, we can think about it here, as we move across, we add more and more positive charge in the nucleus, and then we get increased positive charges holding the electrons tighter and tighter and tighter. So largest elements down here in the bottom. Okay, what about ionization energy? What does that even mean? What is an ionization energy? Energy required to ionize something, right? Really easy name. So specifically, are we talking about forming cations or anions? It is cations, and how did they form the cations? What do we do to the electrons? Yeah, so ionization energy is the energy required to remove an electron, and where do we find elements with the highest ionization energies? Yeah, so top right corner of the periodic table. Why are the trends for radius and ionization energy opposite? Why does that make sense? So here I have a giant fat element, right, with like 8 shells. All the electrons are all the way out on the outside. How difficult is it going to be to steal an electron from that guy? Not very hard, right? It's like babysitting 120 kids. You really can't keep track of all of them. But if I come over here, right, and I've got my really tiny elements holding their electrons very tightly, is it going to be easier or hard to pull an electron out of them? It's going to be hard, right? And wash those electrons. So that's why ionization energy is the opposite of radius. And if you can keep those two things straight, you're in pretty good shape in terms of periodic trends. Any questions about trends I haven't answered?